This is Bruce Carlson, President of Carlson Software. I would like to take you on a brief tour of our new product, Precision 3D Culverts. This is a design tool for pipe sizing, for pond dewatering, for determination of watershed boundaries and peak flow by both rational and SCS methods. And it is revolutionary in that for the first time, you, the civil engineer, the hydrology engineer, are designing accurately in a full 3D environment. Yet the output can be those standard deliverables of plan and profile view that you're accustomed to. But the beauty of this environment is that you do not have to be a CAD expert to accomplish the work. This is accessible to everyone from the technician all the way up to the licensed engineer who thought long ago CAD was beyond them and have delegated so much of the design to junior staff. Now you can take over again and conduct your designs in this environment. Okay, let's talk about the environment. As I move my cursor, notice at the bottom of the screen you see your northing, easting, and elevation. That is calling our surface inspector routine from the office software in a real-time fashion without any degradation of speed in terms of the environment. You even see the flow rate instantaneously for every position, most every position on the DTM surface, because that's calling runoff tracking. Now, if you hover over a area within a computed watershed, you see the subcatchment information at right. And based on whether you're calculating by SCS method or rational method, the peak flow is computed. Note that in this case, we're in a metric environment. So peak flow for this watershed that I'm in right now is computed at 0.157 cubic meters per second. If I move to this pond to the left, if you hover over a water surface where water has ponded up, you see additional information in that right-hand column, which is a tooltip column. Now you see the pond surface elevation, 302.874, maximum depth of 0.135, and volume and area of that pond. Now, the magenta line that you see is the overflow line of that watershed. So that would be the maximum headwater elevation in that particular watershed. The oil tanks are not necessarily part of the surface information. These are objects brought in and placed for greater visual realism. That's accomplished by selecting the object icon, and rather than oil tanks, I could insert a couple wind turbines. So I can place one here, one off in the distance, hit escape a couple times and remove the highlighting, and you can see all the detail of this particular turbine that's been inserted. Objects will cast shadows if you have under Tools, Settings, the Show Shadows option selected. Water can even be moving in appearance. As you get in close, double-clicking moves in close. You can see there's a slight movement to the water that adds to the realism. Now, let's talk about the calculation process here. What we're going to do is begin by removing culvert pipe 3 and highlighting our storm event, which is a rational event. We will rational versus SCS, and we will increase the curve number, or excuse me, the rational method refers to the C coefficient to 0.65. And the rainfall event is itself set under Tool Settings. Right here on the first System tab, the rational rainfall library is selected here. We've selected a fixed intensity rainfall, 5.44 inches per hour in this case, which converts to a rain intensity of 13.818 centimeters per hour because we're set to metric. Now, with that storm event active, we will select one of two pond draining methods. They produce similar pipe sizes, but the volume transfer method moves the water from one pond to another 100% of the water is placed in the downstream pond when a pipe is inserted. So it's sort of a pond dewatering method when you select volume transfer. You click on the Calculate Storm Event icon, and then the calculation occurs. All 50 or 60 watersheds are computed that fast, and the water levels are displayed. Note that you even see subtle aspects of your DTM surface. Here, just below the raised elevated pad, there's a slight extra depression which the water surface manages to wrap around due to the lower elevation there. That kind of detail is revealed in this 3D visual environment. Now the goal will be to place a culvert to drain the pond to the right over to the left. Since we're in the volume transfer mode, observe that pond 0 on the left, and these ponds are just given IDs 0 through whatever. This pond up here would be pond 58, so there might be 100 ponds computed almost instantaneously by the program and given IDs. This just happened to be the first one it ID'd 0. It's got a depth of 0.108. Now watch that depth increase by inserting a pipe and draining from the right to the left. As I move my cursor, the pipe follows the surface elevation. When it's yellow, it's running uphill and warning you. As you head downhill, it sizes correctly, shows a little outflow stream. Let's place it in the base of this pond to the left, pond 0, and we have the instantaneous effect of draining the pond to the right. That visual feedback itself is very helpful to the designer. And now, rather than 0.1 meters of depth, we have 0.444 meters of depth. Let's talk briefly about these perimeter lines in the ponds. The blue line was the original pond elevation. All these ponds that have not been drained will have that blue line. That's where the water ponds up to using the current storm event. The magenta line is the overflow of the watershed, the maximum headwater elevation. The program sizes the pipe on the basis of a design headwater elevation of halfway between the blue and the magenta. But because pipes come in discrete sizes, the pipe that works, that keeps the yellow line below halfway, will in all likelihood pull the headwater line below the halfway point. And let's illustrate this. Let's go over to the calculation mode and do some design work that mimics what was going on automatically with this calculation. Go to Calc Headwater mode, and just like the program tried, try one pipe size down from 30-inch, which it calculated by default. Going to 24, the yellow line is more than halfway. So that's why 24 didn't work, 30 did. And if you change it to 36, you pull the yellow line down even further. Now, because this was such a vast basin, even the 24-inch size would in effect work. So it's up to you to decide what pipe to put in, because the water would only pool to the blue elevation in the peak storm, just taking longer to drain with these smaller pipe sizes. Now, when it's drained, note that we leave behind, look to the right, 0.03 meters of water, just to indicate that that is a ponding area, but has been drained by a pipe. We leave a little vestigial water behind. Now we can continue the process. This middle pond has 0.444 meters. This third pond to our north currently has roughly 0.2 meters. Watch its depth increase as we drain from the second pond into the third pond. There's that blue line that shows you how the water would flow on the lower side, and we'll place it right there, And now the water depth is 0.751 meters, not a full meter of depth, but we've managed to drain the water from both ponds. Now, why does so much water remain in this middle pond? The answer is that it has a 0.03 meter depth, but this middle pond is completely flat. So consider it a feature where you don't see a little localized pool, but instead a broad pool at 0.03 meters. That's just indicating that you have a wide, fully flat area that's showing the 0.03 depth spreading out. Now, there's another thing that we can show, and that is when you move and edit a pipe, there's real-time visual feedback that guides that design. This is a large area to the left, kind of a perched basin that fills with water and might cause problems where it chooses to overflow. So you may also want to have a pipe in to drain this. Let's first place the pipe right about here. And what's going to happen is that this will design a relatively large pipe, as you see here. And the pipe size that it defaulted to was 96 inch. Why? Because it designed in such a way that this pond would not overflow the maximum headwater or magenta overflow level with the pipe selected. It took a very large pipe, given the very small margin of freedom between the base of this area and the maximum headwater overflow. And given that more narrow elevation range, it took a very large pipe, 96 inch, to drain the water. And I would point out that our pipe size in this case is in inches. It's the only thing in English units here, representing perhaps a Canadian design scenario where everything's in metric, but they might be purchasing pipes manufactured with an inch diameter standard. Now, our purpose here is to illustrate moving and editing the pipe. You just grip that little blue cube when that pipe is highlighted there, and you see as you move it to deeper and deeper points, you're in effect vacuuming the water out, which is a very interesting real-time effect of your design. And if we move it to this low point here, we in effect vacuum out all the water, and we've drained this upper area with this larger pipe, preventing overflow, and now the water has found its way into that third pond, even from the upper pond, passed through the middle pond, which is still at 0.03 meters of depth, and the lower pond is now 1.49 meters, containing the water from 3 different ponds being drained. That exercise was very straightforward, highly visual, and when you do File, Save to CAD, you create an XML file that allows importing in other software to show the pipes plotted, and if head walls were inserted, they would plot with their head walls in CAD. And particularly for Carlson software, we create a .sew file which allows plotting within the hydrology module as a pipe network. So there are 2 more videos associated with this one. They will be in English units and illustrate not only the rational method, but the SES method, and the rational method where the return period comes into play due to rainfall intensity tables having greater rain with increasing storm return years.